BIOCHEM. In this video, we get into the gas laws. Ideal gas law coming up. So we will discuss the gas laws in this video. In the last lecture, we covered the different properties of gases. Spent a lot of time discussing gas pressure and volume and temperature, and also the number of moles of gas. So these properties of gases are measurable. You can use a thermometer to measure the temperature. You know, it's pretty simple to get the volume. Lots of pressure gauges will get you the pressure. Moles you can usually measure indirectly. If you know the other three properties, then you can get the moles, and we'll talk about how to do that in just a moment. But it turns out that these properties are related to one another. And if you have a gas and one of its properties changes, then that affects the other properties. And there are simple relations between these gas properties. So let's start off with Boyle's law, which describes the relation that exists between pressure and volume of a gas. Boyle's law tells us that the pressure of a gas is inversely proportional to its volume. So if you have a gas and something happens to the pressure, then that affects what happens to the volume, and they're inversely proportional to each other. What that means is if the pressure goes up, then the volume goes down, okay? And if the pressure goes down, the volume goes up. They're inversely correlated. One goes up, the other one goes down. Now, for Boyle's law to hold, you can't be messing around with the other two properties. So the number of moles and the temperature of the gas have to remain fixed. So as long as those aren't changing, then Boyle's law says that when the pressure goes up, the volume goes down, or when the pressure goes down, the volume goes up. Okay? Now, it's a very predictable effect. If the pressure of a gas is doubled, then the volume is cut in half. And if the pressure of the gas is tripled, then the volume is cut into 1/3. So that's what inversely proportional means. You know, you double this one, that one's now cut in half. You triple this one, that one's now cut in 1/3, and so on and so forth. We can write Boyle's law in a mathematical form as follows. The pressure times the volume is constant. Okay, if you measure the pressure and you measure the volume, multiplying the two, you always get the same number. Okay, P times V is constant. So if you know the pressure times the volume in one situation, and then maybe the pressure changes a little bit and the volume does too, then you take the pressure times the volume in the second situation, you'll get the same answer as you did before. Okay, P1 V1 equals P2 V2. You know, P times V is always the same answer. So you'll get the same answer, you know, in the first situation and the second situation. If you let the pressure change a third time, it'll equal P3 times V3. So that's Boyle's law. Now you can visualize Boyle's law right here. So here we have a gas, and that gas is trapped inside of a piston. Okay, so let's say the volume of the gas is 2 liters and the pressure is measured at 1 atmosphere. Now if you lower this piston and you cut the volume in half to 1 liter, then the pressure is doubled. Okay, so when the gas is squeezed into a smaller volume, you know, the pressure goes up. And hopefully that makes sense, because now all of those gas particles are trapped inside a smaller volume, so you know, the pounds per square inch is going to go up. The PSI is going to go up, or if it's measured in atmosphere, it'll go up. You got more gas molecules hitting every square inch more often, and so you get larger pressure. Cut the volume in half, the pressure doubles. Okay, so P times V equals a constant. Now let's just see that right here. The pressure is 1 atmosphere, the volume is 2 liters. So this times that, 1 times 2, the answer is 2. And over here, the volume changes and the pressure does too, but let's see if we get the same number. 1 times 2 is 2. So yes. All right, here's a little better example. Suppose you got a 4-liter cylinder of helium gas and it has a pressure of 10 atmospheres. Then what pressure does the gas exert if the volume increases to 6 liters? So you're told the pressure and the volume of the gas in one situation, and then you're told what the new volume is in situation number 2. Well, you should be able to calculate the pressure in situation 2 using Boyle's law. You know, if you got a cylinder of helium, then you're not changing the number of moles, and the temperature shouldn't be much different if, you know, it increases a little bit volume. So assume fixed moles and temperature. You can use this equation and you can solve for P2. So here's what P2 equals, P1 V1 over V2, and plugging in the values, you can see the, did I say milliliter? Dang it, that should say liter. This is 6 liters. Why did I write milliliter? Okay, so the liter unit cancels the liter unit, and you're left with atmosphere units, and doing the calculation you get 6.666 round 6.7 atmospheres. Okay, so the volume goes up, the pressure goes down, inversely proportional. The next law relates volume and temperature. Whereas volume and pressure are inversely proportional, the volume and temperature are directly proportional to each other. When one goes up, the other one goes up. And when one goes down, the other one also goes down. Okay? And if suppose the temperature is doubled, the volume doubles. If the temperature triples, the volume triples. Now your temperature's got to be in kelvins for this, you know, to work. Okay, you got to have an absolute temperature scale, more specifically. And the mathematical form for Charles' law is the volume divided by the temperature is constant, or V1 over T1 equals V2 over T2. The fraction always gives you the same answer, in other words. For Charles' law to hold, you cannot be messing around with moles or the pressure. Okay, so N and P are fixed. And I do have a picture of a Charles' law situation. So here's a balloon, okay, filled with gas, and it's been plunged into ice water and then boiling water. So if it's a sealed balloon, you're not changing the number of moles, and since the gas is in a balloon, the pressure remains constant. The pressure of the gas inside always matches the pressure outside, okay? So that's the thing about a balloon. A balloon expands and contracts because the pressure inside always has to match the pressure outside. When you plunge the balloon into ice water, you know, the water cools the gas down, and these molecules move more slowly. Okay, so they're not moving around as fast inside, and so they're not colliding with the walls of the balloon as hard, and so they're not pressing the balloon out. So slower moving gas molecules, you know, the balloon's going to contract. Okay. Now, if you take that balloon, you plunge it into boiling water, then the gas molecules move more quickly. They strike the balloon, and they make it expand. And the balloon grows in size. So if you, again, double the temperature, then the volume would double. Now, suppose we do have a 1 liter balloon in ice water. Then how many liters is it in boiling water? So let's solve that balloon problem. You got a 1 liter balloon in ice water. How many liters is it in boiling water? Well, you need to know the temperatures of ice water and boiling water. In ice water, that's 0 degrees Celsius. You know, that's the temperature at which liquid and ice is at an equilibrium. That's 0 Celsius. Water freezes at 0 Celsius. So ice water is 0 Celsius. Boiling water is 100 Celsius. Converting those to Kelvin, that's 273 Kelvin and 373 Kelvin. Now you have the volume of the balloon at this temperature, and you're told what the new temperature is. You should be able to calculate the new volume using Charles' law. So this time we're solving for V2, okay? V2 right here, and here's V2, and plugging in T2, T1, and V1. So here's T2, T1, and V1 all in the proper units. The Kelvin units cancel, and you're left with liters, and doing the math you get 1.37 liters. So you see the balloon grew a little bit. You didn't really double the temperature, so the volume of the balloon's not going to double, but you did increase the temperature somewhat, so the volume will increase somewhat. So that's Charles' law. There are some other gas laws that the textbook mentions, and I'm not going to discuss them too much, but I'll mention what they are. Gay-Lussac's law relates the pressure and the temperature. If you fix the number of moles and volume so they remain constant for the gas, and you allow the pressure and temperature to adjust, well, you'll see that the pressure is directly proportional to temperature. If the temperature doubles, the pressure doubles. So if one goes up, the other one goes up proportionately. And if one goes down, the other one goes down proportionately. So, doubling the pressure or doubling the temperature doubles the pressure. If you cut the temperature in half, the pressure gets cut in half, and directly proportional relationship. And it's P1 over T1 equals P2 over T2. That's the mathematical form. Avogadro's law, or as we like to say here in Hawaii, Avogadro's law. Avogadro's law relates volume and moles of gas. Fixing the pressure and temperature makes the volume directly proportional to moles. If you double the moles, the volume doubles. If you cut the moles in half, the volume gets cut in half. Okay? Hopefully that makes sense. You can imagine a balloon again. Suppose a balloon's got, 1 mole of gas. It occupies a certain amount of volume. If you blow in more gas, you double the amount of moles of gas, the volume's going to double. Okay? So directly proportional, one goes up, the other one goes up, one goes down, the other one goes down. Again, the fraction is the case. So V1 over N1 equals V2 over N2. So lots of gas laws, Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law. There's maybe a couple others that we don't need to mention. But you should be able to, you should have them written down somewhere so you can reference them when needed. Boyle's law is pretty common, and you'll see that used quite a bit. The big one is the ideal gas law. Okay, it turns out that you can even derive all of the other laws from the ideal gas law. This is the most important one, and this one relates all 4 gas properties at the same time. It works for any gas, or even a mixture of gases. And what the ideal gas law says is, if you have a gas, any gas or mixture of gases, if you take the pressure, if you measure the pressure and you measure the volume, you measure the number of moles and you measure the temperature, if you calculate this fraction, then you will always get the same answer, R. R stands for 0.0821 atmosphere liter per mole Kelvin. So that's telling you the units for which you want to measure the other ones in. You got to measure the pressure in atmospheres, the volume in liters. This is counted in moles, the number of particles in moles, and temperature must be in Kelvin. If those are the units you're using, you calculate this fraction for any gas, you will get that answer. So let's go ahead and use that equation. This is called the ideal gas equation. Let's calculate the volume occupied by 1 mole of CO2 gas at 0 Celsius and 1 atmosphere. Now, notice that you're told the number of moles, N, the temperature, T, the pressure, P, and you're asked for the volume. And And that's usually how you use the ideal gas law. You're told 3 of the properties, you get the 4th one using the equation, because you always know what R is. If you know what R is and you know what 3 of the properties are, then you can solve for the 4th property. So solving for V, that's how you'd calculate it. Just make sure that the other properties are in the correct units. So it looks like your pressure is in the correct units, but your temperature's got to be in Kelvin. So 0 Celsius, convert it to Kelvin, that's 273 Kelvin. It's very simple to get from Celsius to Kelvin. You just add 273. So when we plug in the temperature, we're going to plug in the Kelvin temperature. Okay, to calculate the volume, it's going to be number of moles, 1 mole, okay, times R is 0.0821. Here are the units of R. The temperature is 273 Kelvin, and the pressure is 1 atmosphere. Okay, and you can see the units here, canceling the units of the gas constant, and you're left with units of liters, and you calculate 22.4 liters. Now, this is an interesting example because, you know, many gases are studied at 0 Celsius and 1 atmosphere. This is called standard temperature and pressure. Right, so gases are often studied under standard temperature pressure conditions, or STP conditions. And so now we know that if you're looking at a gas under STP conditions, 1 mole occupies 22.4 liters. If you got 2 moles of gas under these conditions, it's going to occupy twice that much. Okay, 44.8 liters, using Avogadro's law, right? You know, you double the moles, you double the volume. So anyway, typical ideal gas law example. Let's do another example. How many moles of gas are contained in a typical human breath that takes in 0.5 liters of air at 755 millimeters mercury pressure and 37 degrees Celsius? So a person inhales a half of a liter of air at this pressure and temperature. Okay, this is about body temperature, by the way. 37 Celsius, roughly the temperature of body. 755 millimeters of mercury, that's, you know, roughly the temperature of an average day. Maybe a little low, maybe it's rainy outside, low pressure day. But anyway, you inhale this much air at this pressure and temperature. How many moles of air did you inhale? Well, using the ideal gas equation, PV equals nRT, you solve for N, and that's going to be PV over RT. Okay, this is what it likes when you. This is what it looks like when you solve for N. Now, we got to make sure the pressure, volume, and temperature are in the correct units, and they're not. The volume is correct, but the pressure needs to be in atmospheres and the temperature in Kelvin. So let's fix the two. To get from millimeters of mercury to atmosphere, you know, 760 millimeters of mercury is 1 atmosphere. So here's the conversion factor. Units cancel and you get atmosphere. So that's how many atmospheres it is. And to get from Celsius to Kelvin is simple. You just add 273, and that's how many Kelvin it is. Okay, so we got the correct units now. Let's plug in the properties. So here's the volume, 0.50 liters. The pressure is 0.9934 atmospheres. R is 0.0821 atmosphere liter per mole per Kelvin. And temperature is 310 Kelvin. And you can see your units canceling, get the moles in the denominator of the denominator, so it comes back up. You're going to end up with moles, and the calculation gives you 0.01951 moles, which rounds to 0.02 moles. By the way, the air that you breathe in is mostly nitrogen and oxygen with a little teeny bit of CO2 and maybe trace amounts of other gases. You know, and the air that you breathe out is a little bit different. Some of that oxygen has now been converted into carbon dioxide through the chemistry of your body. You know, so the air that you breathe in might not be the exact same as the air that you breathe out, but at least we know how many moles it is. You're taking in 0.020 moles and you're exhaling 0.020 moles. Okay, so we've calculated the number of moles. The last law that we discuss is Dalton's law of partial pressures. Dalton's law is a pretty simple law. It's a little different than the other ones. It deals with mixtures of gases, okay? Kind of like the air that you breathe in and breathe out. You know, the air that fills up the atmosphere is a mixture of many different gases. And, you know, think about a mixture of gases. You got lots of different types of gases occupying the same container, okay? Each individual gas can be considered separately. And they all are exerting pressure on the container walls, okay? And you could think of, well, if I just, you know, if I got like a, you know, one gas, you know, what pressure does it exert? If I could somehow delete the other gas molecules, you know, what's the pressure of just that one particular gas? We call that the partial pressure of that gas. So if you have a gas that's made of a mixture of many different gases, then the total pressure of the gas mixture is simply the sum of the partial pressures of its component gases. So if you got, you know, the total pressure, you can say that it's going to be the pressure due to gas number 1 plus the pressure due to gas number 2 plus the pressure due to gas number 3 plus however many you know, gases you have. Now here's an example. So let me move myself up here. Okay, up to the top. Whoa! So okay, I had to make a little room. I can't scroll this up for some reason. Okay, our last example in this lecture. It's going to use Dalton's law of partial pressures. A scuba tank contains 3,200 psi of air. Okay, lots of stuff in the air. It's a mixture of gases. A scuba tank contains 3,200 psi of air. If there is 2,080 psi of nitrogen in the tank, then how much psi is due to oxygen? Okay. Now here we're making an assumption the tank only has nitrogen and oxygen. Okay, so suppose you know, the company, you know, makes these scuba tanks and they control what goes in there. They put nitrogen and oxygen. Okay, they fill it up to 3,200 psi and you're told how much nitrogen is in there. So what amount of oxygen is in there? How much psi is due to oxygen? So in this case, the mixture only has two component gases, nitrogen and oxygen. The total pressure would be equal to the partial pressure of the nitrogen plus the partial pressure of the oxygen. And so if you want to solve for the partial pressure of the oxygen, this is a typo. This should say P of oxygen equals P total minus P of nitrogen. I got it backwards. Dang it. Okay, the partial pressure of oxygen, that should say O2 equals the total pressure minus PN2. We're going to pretend that this says PO2 equals PT minus PN2. So I solved for the wrong one here. It's like the fourth typo that I've noticed in recording these videos today. PO2 equals the total pressure minus PN2. So you take the total pressure and you subtract PN2. And 3,200 minus 2080 is 1120. And that would be the pressure due to the oxygen. Okay. Now that we know the partial pressures, we can you know, ask a little bonus question here if we like. What percentage of the tank pressure is due to the oxygen? Okay. What percentage is due to oxygen? Well, the percentage of the pressure that's due to oxygen would simply be its pressure divided by the total pressure times 100. You know, the part over the whole times 100 is the percentage. So you take the oxygen pressure divided by the total pressure times 100, you get 35%. oxygen. And you can see that's much higher than the normal amount of oxygen in the air. You know, when you're breathing in air, you're breathing in about 20% of the pressure is due to oxygen. Okay, now if you have a scuba tank that contains a little bit enriched oxygen in there, that can help you hold your breath for longer. You got more oxygen that you're breathing in, you know, that's more going to your body, and you'll last for longer under the water. So there are enriched oxygen tanks out there, probably a little bit more expensive, you know, to purchase that type of air, but you know, it's cool that you can get that. Extra O2 can help. So that's it for the gas laws. What comes next? Intermolecular forces. So stay tuned for that. Aloha.